So we will start now. Can you hear me, all of you?
Yes, sir.
Yeah. So we'll start. Uh, Maybe recall not yesterday, last class, and let us do it for a few minutes. We were dealing with a spherical particle in one dimension. We had the Stokes law, where the viscous drag is given by 6 pi eta r. R is the radius of the particle times some velocity v0, velocity of the particle. Okay. Then we had done this, and we had shown how to actually estimate, for example, Avogadro's number just from measuring this mean square displacement of the particle. Okay. And then we had started this single particle level description, which is slightly different from the Einstein description, which is based on the probability distribution, how that probability distribution changes as a function of time and space. But here it is at the single particle level. This is due to Langevin. We had shown that if you don't have this random noise in the equation of motion, then the velocity will decay very, very fast. So it will velocity will be almost zero within fraction of second, 10 to the minus 7 second, velocity is almost zero. So there has to be a mechanism by which the particle is made to move even if I wait for long enough time. So it is always moving, it is always in motion. So this is because this is done by introducing a random force in the equation of motion. So we had this random force in the equation of motion. Then random force means if you take an ensemble average of this, it's equal to 0. And this has a special correlation is given by some kind of C or C prime, whatever you want to call it, some constant, 2 times this constant, delta t minus t prime. Delta is a Dirac delta function. So only when t is very close to t prime, actually t is equal to t prime, you have correlation. Otherwise, there is no correlation. This is called white noise, actually. There's a name to this. It's called Gaussian white noise. It is a Gaussian distribution, and it is white because there is no memory. Memory in the sense, this noise correlation is a delta function. It is not a function which is which will decay with time. It is picked at that t minus t prime, t equals to t prime. Otherwise, it is 0. And then we did a little bit of algebra and all those things, and we came up with this very nice expression for the mean square displacement of the particle. The general expression, this is how it is given by this expression. And we had shown that in the long time limit, it becomes linear in time with this constant, 2 times this constant times time. This constant called diffusion constant or diffusion coefficient. This kBt by 6 pi eta r. And in the short time limit also, you can analyze this mean square displacement, and it shows that it has t square kind of behavior, which is ballistic. So in the short time limit, it's ballistic, t square. And then in the long time limit, it is diffusive, which is proportional to t. Okay. So I think we had gone up to this, no? And so we'll start today. So let us start here. Today, the first initially what I'm going to do is very, very important for this course, for this part of this course. We are going to talk about something like the relation between the random noise or the random force and the viscous force. Okay. And this relation has a name, and this is called fluctuation-dissipation theorem. This is very, very important in time-dependent statistical mechanics. FDT, fluctuation-dissipation theorem. I don't know whether you have heard about it. Has anybody heard about it? FDT? Did anybody know about it? You can unmute and tell if anyone. Nashid, did you know about it?
No, sir.
Okay, so it is new. Okay, good. So let us try. So let me start by writing the Langevin equation. Okay. So let us write the Langevin equation. What is the Langevin equation? If you write it down, it is dv dt equal to minus eta r v by m. This is the equation. You can go and check your class note. Okay. And I defined a constant, which is, I think we also had done it earlier. I'm calling it gamma. 6 pi eta divided by m is gamma. So then this equation becomes dv dt. This is not new. This is v. It doesn't look like v. Let me do a little bit so it looks like v. Okay. This is minus gamma v plus ft divided by m. Okay. Now I just multiply both sides by v. If I multiply both sides by v, what I'm going to get? I'm going to get v dv dt is equal to minus gamma v square plus 1 over m. You can take it like this. V means v at time t. Okay. This is how it is going to look like, isn't it? Now, after doing that, I can also, if you look carefully, what is this? You know that if I have d dt of v square, this is 2v dv dt. dv dt. This is very simple. So v into this one is actually, you know, what is this? It is half of v into dv dt. So v of dv dt is half of this. So I can say that this is equal to, I hope I can just write like this. From here I can write like this, that if I write d dt of v square, this minus, I have to multiply by 2. Hope this is fine. This is very simple. Okay.
Yes, sir.
And now I take ensemble average on this. Now if I take ensemble average, what I'm going to get? I'm going to get and for next 10-15 minutes or so, we'll see how to evaluate this integral. Not integral, rather this correlation function.
So, why can't we simply say that velocity and random kick are not correlated?
Yeah, because position and random kick are correlated. Velocity and random kick are may not be correlated. Could be correlated. We'll see. Because because it is at the equal, it is equal time correlation. No, it is velocity at time t and random kick at time t. It is obvious that because if I go slightly away from t, there will be correlation, because it depends on the random kick what will be the future velocity, isn't it? If I go to t plus delta, then that should be a correlation. So you don't even know when both are equal whether there's a correlation or not. We'll see that. Okay, try to see what happens. So we have to calculate this. So before we calculate, let us do this. Now we know that if I, for example, take this v dot and integrate this from, if I integrate this from t minus delta t to t, what will be the result? This is nothing but Vt. Fine, this is very simple, no?
Yes.
Now I multiply both sides by f of t. And taking average. Same. Okay. So from here I had written, let me write down, this is the equation, Vt equals to okay. Is this clear? Now I just multiply this with f of t. So this thing will become f of t Vt on your left. Is this fine? Take average. F of t. Okay. This is the thing, isn't it? It's very simple what I'm doing so far.
Yes, sir.
Now what about this first term on the right hand side? Just look at this term very carefully. As Anish was asking, this term is actually 0. Why? Because as the velocity at earlier instant, which is your, and of course your t minus delta t is less than t, has no dependence on the future fluctuating force. You understand this statement? See, this is velocity at say t equals to 10 to the minus 7 second, and this is random force at t equals to 10 to the minus 8 second, whatever, later time. They are not correlated because the velocity at earlier instant has nothing to do with, it cannot decide what will be the future fluctuating force. So that as a result, so this correlation is 0. This correlation is 0. Okay, so we put this correlation 0. If we put this correlation 0, what I'm going to get, I'm left with this, only this integral part, no? Okay. And now what I'm going to do, I'm going to use my knowledge of Langevin equation. So just I'll use Langevin equation. What I have on my left is Ft is equal to, let me write down one more time. This is what I have, no? Now you know V dot T. I can replace V dot T, no? Because I know the equation of motion for V dot T. What is that? Minus gamma Vt prime plus
Ft prime
by m essentially I have this, no? So now I'm going to split this into two. The first one is going to be gamma, you can take it outside. Now, what about this? The first term. Can you comment? See, just look at it. T prime varies from T minus delta T to T. So T prime is always less than T.
Hence the correlation is zero unless t prime equal to t.
Yes, but then when T prime equals to T, your integral is 0.
Yes.
Okay. So I should write down. So let me write it down. Uh, since T prime is the earlier time less than T, and the fluctuating force, let me write it down, is very important, is at a later time has no dependence on velocity at T prime x except at T is equal to T prime, for which integral is 0. Okay, is this clear? So now actually I much better now, isn't it? What I have here now, on my left hand side I have Vt Ft equals to 1 by m T minus delta T into to T okay, fine.
Yes, sir.
Now the kind of theory you are doing, the system you're dealing with, will assume there is something called time translational invariance. Okay, in other words, we'll assume that the random noise this Ft is stationary in time. So this means the value of the integral depends on the difference but not on T and T prime individually. So is this clear, this statement? So let me tell you, if I have this force f of t as a function of time, so this is like this, no? This is f of t as a function of time, random, and I want to calculate its correlation function of this force. Say I take one point here and another point here. This is T1, this is T2. And in another case, I take, say, one point here, this is your T1 prime, and one point here, T2 prime. Okay. Now, this correlation between these 2 points has nothing to do with the value of T1 and T2 or T1 prime or T2 prime. It actually depends on how much they are separated in time. Is this clear? So if I take a segment, if I assume that delta T is the segment, which is T2 minus T1, which is also equal to T2 prime minus T1 prime. Doesn't look like, but it is okay. Then if delta T is the same, then the correlation between these 2 points will be same. So only how much they are separated in time, that matters for stationary random force. This is called time translational invariance also. The invariant under time translation. Is this clear?
Yes, sir.
So if I calculate the correlation function between 2 points in time, it does not matter on the absolute value of these 2 time, but what matters here is how much they are separated. It is a time difference, T2 minus T1. In this case, T1 prime, T prime minus T. That matters, or T minus T prime. That matters. Not the absolute value of T, not the absolute value of T prime. Is this clear? Very important.
Yes, sir.
If this is the case, then the above integral, let me write it down again. This above integral, I can write it as this just a trick, so that I have a symmetric interval. Okay. And this one also I can write it as where you, and then this one I can write it as so you can see what I have done, because this correlation function depend on T and T plus S. So the difference, what is the difference? S. So this should be equal to F0 Fs, isn't it? Because here the difference is also S. And then what I have done, that T plus delta T I replace with infinity, and T minus delta T I replace with minus infinity. Okay. So I have done 2 things. Number 1, since delta T is much greater than whatever we put, okay, this is number 1. And number 2 is what? Without any loss of generality, we may put here. Okay. If you have any question, please ask me.
Why is delta T much greater than S?
Because the correlation, I always, whenever the AS is running, no, this is a integration
Variable.
yeah, it's the integration variable. So delta T is always has to be, because you have to, whenever you integrate this, you integrate like from some initial, how should I put it actually? Your AS is what? AS is your T prime minus T. It's a segment. This is your S, no? This minus this is your S. This minus this is your S, isn't it? So usually whenever you look at the correlation, look at the correlation where these two events are separated by a finite time, isn't it? So S is finite. Is this clear? S has to be finite. If it is
Yes.
very, very long, it is expected that correlation will be lost. So delta t is the limit. So basically, and delta t is what? Delta t is actually, I'm assuming a limit where delta t is so huge that the correlation is lost. So that's why it is put this integral, this minus infinity to plus infinity. Long time the correlation is lost. So delta t is much, much greater than this running time difference S. Okay, this is clear. Maybe you can think about it and get back to me. I'll try to give you a better answer.
Also, it should be t prime equal to t plus s, right? If we
Yes, t prime equals to t plus s, and then the next step is your just I take t equal to 0. So it is f0 and fs, because this is time translational invariant, no? Your correlation.
yes, I'm just saying it should be a correction to what you've written after the semicolon.
After the
Semicolon.
yes, t equals to t prime plus s, no? Any
No,
problem?
t prime equal to t plus s.
Yeah. Sorry. Yeah. T prime equal to t prime. Yes. Okay, I'll do that. That doesn't matter actually here. It doesn't matter, isn't it? Does it matter?
Yes, no, it doesn't really matter.
Yes. Yeah. Anyway, so after that, okay. So now we get back to the Langevin equation. What we had, if you go to your Langevin equation, you had from the Langevin equation you had this, no? And then here you had what? Remember 2 by m. That is what we have, no?
Yes.
Let me do it. And what I'm going to get here, it should be 1 by 2m, and it should be okay. This is clear.
Yes.
What about this quantity? The v square average, you know, because you are in equilibrium. You assume in equilibrium, no, all the time. So this is 0. This is
Yes.
0. So what I have here, this 2 and 2 will cancel. You have 1 by m square, whatever. So what I have here is, actually like this. I can express gamma. So your gamma is going to be equal to 1 by twice yes, because let me write it down here, minus 2 gamma into kBt by m. So if I take on the other side, 1m will cancel, no? So we'll have kBt m. This is how it is, isn't it? So you can see that we're expressing gamma, which is your something like friction, isn't it? Dissipation, related to the dissipation. And the correlation between the random forces. And this relation is called fluctuation-dissipation relation, dissipation theorem.
Hello,
Now,
sir.
what does it mean physically? Yes, somebody has a question. Yes.
Sir, in the Brownian motion, sir, we have a constant like random force.
Hmm.
So why do we consider it to be equilibrium in
It is always in
equilibrium?
equilibrium. So even the Brownian motion theory is also in equilibrium. Even see, the point is as follows. Even if you have random force, even if you have dynamics, you're looking at the dynamics which is in equilibrium. Because all time you have this fluctuation dissipation theorem valid. As long as this fluctuation dissipation theorem is valid, it ensures that in the long time limit, if you wait sufficiently long, you will get equilibrium. So very good example would be if you take harmonic oscillator, a Brownian particle trapped in a harmonic well. Okay, it is also experiencing random kick from the environment, and then you calculate the distribution, the probability distribution, isn't it? P of x comma t, which you have not done for harmonic oscillator. If you do it, then you will see that if you take t goes to infinity limit, that distribution becomes equal to Boltzmann distribution. It ensures equilibrium. So you're always very close to equilibrium, slightly away from equilibrium, but your fluctuation dissipation theorem is valid. So
So
in it,
this is like what we were talking about near equilibrium in the beginning of the class. This
yes,
is an
yes,
example of it.
yes. So I would call it equilibrium. It is not truly non-equilibrium. Okay, a truly non-equilibrium situation would be something where you don't have this FDT valid. If you break this FDT by hand, then you are not in equilibrium, because that will ensure that even if you wait long enough, you'll never achieve equilibrium. So in our lab, I think some of my students are actually working on this truly non-equilibrium system. One example is active particles. So actually, I'm going to give a talk on 9th in the department. So if you have time, please attend. So if you don't have class, 4:30 Friday. Okay, so if you are chemistry department, it will be a short talk, half an hour talk. Anyways, so now what does it mean physically? That is very important. This is a mathematical relation, no? Mathematics is important, physics is even more important. Huh? What does it mean physically? So it basically means there is a balance between dissipation and fluctuation. That is what this theorem is all about. See, when the particle, your system is your Brownian particle, it is undergoing this zigzag motion. What happens? Uh, it gets random kicks from the environment, no? So energy flows into it from the environment. Also, it dissipates energy to the environment, and there's a balance between the energy flowing into it, into this particle, and the particle dissipating energy to the environment, isn't it? This balance is given by this FDT, and this ensures equilibrium. Is this clear?
Yes, sir.
Any question? This is very important. So we are still very close to equilibrium. Brownian motion is not truly non-equilibrium. It is close to equilibrium. Okay. Now we'll do a few more things. Now recall, we had started with this correlation. Remember this correlation? We had said 2C prime delta function, isn't it? Remember? Check your notes.
Yes, sir.
Okay, wait for a few minutes. If I write too much on a page, there is some problem. So I can go to the next page and write it here. Okay, so we had this correlation that if 0 fs doesn't matter in which order we write in classical. Yes, this is how it is, isn't it? Okay, go and check. You had like t minus t prime. Here it is 0 minus s. So if I now put it in that expression, what I have here is what will the answer? And 2 will cancel, no?
C prime by 2 kbtm.
C prime by kbtm, 2 will cancel. And delta function, if you integrate, I'll get 1, no? Okay? So exactly I put this. So now I have gamma and C prime, the relation between them. So what is C prime then?
Gamma m kbt.
And you know gamma, what is gamma? So what I have here is C prime equals to, this is actually another form of, special form of FDT, you can call it. Another way of writing a fluctuation dissipation theorem. Look at very carefully what I have achieved here. Okay, the color has not come in. Because it tells you that if I have a correlation in general, this correlation is actually twice gamma, small gamma I can, kbt, where your small gamma I can call it, this is friction or friction coefficient. Okay, so what does it tell you? It tells you that your strength of this noise correlation cannot be arbitrary. Is this clear? It has to be proportional to the temperature and the gamma friction. Is this clear? That ensures equilibrium. So if I now take not this, some other constant which is not depending on temperature, doesn't depend on temperature, then it will break FDT, isn't it?
Yes.
So this is very, very subtle thing. You should notice. This is very subtle. So this is also another way of writing your FDT, fluctuation dissipation theorem. I want to remove this. Leave it. It's not working. Okay. So now so far we have been doing this Brownian motion in coordinate space x. The next thing I'm going to do, we're going to talk about is Brownian motion, but not in coordinate space, but in velocity space. This is quite important. I'll tell you why. Not today, maybe next class you'll know why. Now we go back to Einstein's version, Einstein's treatment. Just recall. In the coordinate space, we have done something like this. In the coordinate space, you had done something like this. If you see your note, you'll see. Remember this? And delta was jump in coordinate space, isn't it?
Yes.
And from here you had derived Einstein's equation, diffusion equation. It was something like this, which is to a physical chemist, it is like fixed second law, isn't it? How many of you know fixed second law? Fine.
Yes, sir.
Okay. Now, here we are going to do something else. We are going to do things in the velocity space. And we'll use this notation. Say I want to know what is the probability distribution in the velocity space. No x but v. And I just follow this notation that okay, you start with f with velocity v minus delta. I can have it minus delta, and this phi. Now the jump in this case, earlier jump depends only on delta, doesn't depend on the position. But here the jump should depend on with which velocity it is jumping. Okay, so it depends on v minus delta. Of course, how is the jump? What is the jump magnitude? It depends on this. Is this clear? This is the relation in the velocity space. And I'm not writing what is this. This you understand, no? Jump probability. Exactly yes. Like what I have done, what we have done in the coordinate space. Okay? Then what should I do next? I should do something like Taylor expansion. We should expand around time t and around velocity v. So on the left hand side, what I have, I'll have something like f, which is v comma t plus tau and on the right hand side, what I'm going to get, right hand side I'm going to get you see carefully, you have things in the integral. So let me write down which is outside integral, the integrand. Let me write down the integrand first. Integrand is going to be f v comma t just a minute, wait. Yes, v comma t, because you had this, no, essentially a product of these two, no, it will be minus but one thing you remember, the delta has a dimension of velocity. This is not position, not in the coordinate state, a coordinate space. Okay, this should be clear to all of you. This one, and then I'll have other higher order terms. Okay, let me write down in a actually. So let me write down this, the terms separately. Okay. Yeah. Yes. By 2. This should be multiplied with phi sorry. Sorry, it should be v. This should be v, this should be v. For some reason, I'm having some problem in writing. Okay. But again, I don't take this to term. I just take only this. So this will give me okay. I don't take the other terms. Now this will go inside the integral. So if I write RHS carefully, so the first term in the integral it is going to be, see, this integration is over delta, d of delta. So I can take this guy outside. It will be, is this clear? Anish and others. What is the next term? What is the next term? Next term is, you know this, you have del del v, of course, with a minus sign. And then you have f, which is a function of v and t. And then you have an integral, which is then I have another term. What is that? Okay. What about this integral, the first integral? This one. What about this? Recall your part.
Equal to 1.
Is equal to 1, no? Because it is normalized, no? The jump probability, no?
Yes.
It has to be 1. So now what I have here on your, this one and this one will cancel, LHS and RHS. Okay?
Yes.
And I don't take this is very small. So I have this tau times del f del tau, whatever. Not del tau, this should be del t, del f del t. Huh? Is this clear? So
Yes.
on your right left you'll have del f del t, but then I can divide the whole thing by tau. So I'll get something like this. On your left, right, it will be okay. Okay, is this clear?
Yes.
And this part I am calling it this integral with 1 over tau. This I am naming it as m1 v, and this one I'm naming it m2 v. Then I can write down this equation again. Now this is going to be and this term is called the drift term, and this m2 is called the diffusion term. But again, we're talking about diffusion in velocity space. This is not physical diffusion in space, in position space. It is diffusion in the velocity space. Okay, there is no position here. Little abstract. This is clear. Is this clear?
Sir, is the phi of delta an even function?
Yes, I would say, because it doesn't matter. The magnitude of velocity matters, not the direction.
Then integral delta phi delta delta is supposed to be zero, right? If phi delta is even.
Uh, mm, yes, but in this case it is not. So it is not a. Then it is. I should correct my statement. Yeah, in this case it is not. When you talk about velocity in the diffusion, the velocity space, in this case it is not, because your average delta, your average delta is non-zero. It is not.
So there is some influence of direction on the probability of that jump.
Yes, it has some influence of direction in the probability of jump. Okay, we'll talk about it, yeah, when you evaluate this. Yeah, good question actually. So now this equation has a name. I don't know whether you know this equation, the name I'll tell you. Yeah. This equation has a name, and this is called Fokker-Planck equation. Okay, how many of you heard about it, this equation? Did you know, any one of you? Did you know, any one of you, or you have not? You did not know?
No, sir.
Okay, so let us now calculate these quantities, the m1v. So we had this equation, no? dv dt equals to minus gamma v plus. This basically implies now integrating. If you integrate this way, the way I'm doing, so it will give you v, but v at t plus tau minus v at t on your left. This is equal to minus gamma v t plus tau minus t, which is tau, plus 1 over n, we can take it out. Okay. Now this one, this vt plus tau minus vt, this is your delta. Okay, this part is delta. Now if I take average, what is going to happen? This is minus gamma v tau. I assume within this limit it is moving with a constant velocity. What will happen to this? This is going to be 0, because f average is 0. So your delta average is minus gamma v tau. Just one line. This is called the drift term actually. Gamma v tau equals to delta average. This is the drift term you have to wait because so now you know what is M1V. Can you tell me what is the value of M1V then? What is the value of M1V? The term?
Minus gamma beta.
See, you had I don't know what is happening. Oh, it has come now. There's a gap. Okay, I'll just go to the next slide. This is the problem. Sometimes we have this problem. It's a gap. Because your M1B is just your delta average divided by tau, isn't it? That is how you calculate the average. This is the problem. This. Sorry, some problem with my computer. It is refusing to write. Let me see if it's what. Yeah, now. Because I wanted to finish this. I wanted to calculate the second term also. I can't even change. Ah. So basically, if you calculate this y tau, you just see exactly this is what your M1B is, isn't it? M1B was nothing but, and this is exactly what you have calculated here, minus gamma times B. Is this clear?
Yes, sir.
Now you calculate M2V. Second term, this is called a diffusion term. How do you calculate this M2V? I go back, my delta expression was like this, gamma V tau plus at this. So if I make a square of delta, It will be of course plus minus 2 gamma g tau divided by m and then I have this something like, what is this function gt, the function of tau is equal to t prime. Is this fine? This is a my, essentially I do a plus b whole square of this,
Yes.
a square plus b square minus 2ab. Okay, a minus b whole square. So now I take, now tau is small. If tau is small, then the first term can be neglected. If tau is small, you can neglect this term. No? So then you have delta square is this plus this. So the average of delta square will give you, and also average of ft is 0. The second term will be 0, isn't it? So average of delta square is going to be what? It's going to be average of gt square, isn't it? How do I write down? Gt square means 1 over m square have to have ft prime. Is this clear? What I've written here? I've used two dummy variables, t prime and t double prime.
There should be a dt double prime.
Yeah,
right?
I have to write somewhere. Yeah. So this is how it is. Okay, is this clear?
Yes.
And now I go to this next slide. So what I have here is delta square average is equal to 1 over m square okay, and this one you know what is that? It is 2 c prime delta function, no?
Yes.
Now can you tell me what is the answer? See, one integral is going to be 1, isn't it? This delta function.
Yes.
And then I'll left with one integral which is integral in time. So this will give me t plus tau minus t, which is
Tau.
this is the answer. So basically this one is this. So if I calculate delta square by 2 tau, this is going to be c prime by m. And this will be something like the diffusion coefficient, isn't it? But in the velocity space. Of course, m square should be there. Is this clear to all of you? This is the diffusion coefficient in the velocity space. Because this is ever mean square displacement, no? Divided by 2 times time, that gives you diffusion constant. Remember, x square average is equal to 2dt. With that analogy, I can say something like diffusion constant, but in the velocity space, but
Yes,
not
sir.
in the coordinate space. Okay. So now the next thing is to evaluate so let us come back to the Langevin equation. The Langevin equation, we had this. Now if you integrate using integrating factor, you know this, no? All of you, I think you should know. formally, then this will be Vt equals to V0 exponential of minus gamma t plus exponential of minus gamma t divided by m 0 to t, you can call it exponential of gamma t prime f t prime to t prime. This is the general solution to this differential equation. Anish, you can go and check. All of you can go and check. This
Yes,
is
sir.
fine. This is fine with you.
Yes, sir.
Yeah. So now I take this Vt and V0 on the other side. And I have taken and square it and averaging it. So if you square it, this is okay, and you're averaging it. Okay, remember that you're averaging it, but squaring it also. Squaring it means you have to integrate, you have to use these two dummy variables. So you'll have gamma, and then average is over this noise, isn't it? The fluctuating quantity. Is this clear if I write like this?
Yes.
And you remember what is this expression? This 2c prime delta t prime minus t double prime, isn't it?
Yes.
So the high here is this. So now I can take 2c prime outside. Now look at it. I can integrate over t double prime, for example. If I integrate, what I'm going to get? I'm going to get this t prime should be replaced by t double prime, isn't it? Sorry, t double prime should be replaced by t prime.
Yes.
So I'll have e to the power of 2 gamma t prime,
DT prime.
isn't it? Exactly what I should have this. And if I write it down again, what I'm going to get 2 gamma t prime, and let me minus. Now this one will give you e to the power 2 gamma t minus 0 is 1, but you will get 2 gamma also, no? And then you can multiply this inside. What I'm going to get 2 will cancel. You'll have m square, of course. C by m square, you have gamma. This will give you 1 minus e to the power minus 2 gamma t. Clear? So I'll
Yes.
should be clear, I think. So what I have here is this. On my left hand side, I have Vt minus V0, sorry, average. This is equal to what I have here is C by gamma m square. This is exactly what I got here, no? C by gamma m square.
Yes.
Okay, now if I consider a long time limit where t is much greater than 1 over gamma, then what will happen? Then this part will be 0, no? Minus 0 minus gamma t. So I have on the left hand side, I will have Vt square average. This is equal to C by gamma m square. Long time limit, no? Okay, is this fine to all of you?
Yes.
So C by m square is now gamma times B square average. Now what is B square average? It is KBT by m, isn't it?
Yes.
And what is C by m square? You remember, recall? Let's go to a couple of slides back. What is C by m square? It should be somewhere here, yes. Not C, C prime actually, anyway. This is delta square average by 2 tau, isn't it?
Yes.
Should put prime. This is my notation. And you know, this is nothing but your delta square average by 2 tau, which is your m2v. And that is equal to, so now I have also got the expression for m2v, isn't it? And m1v was minus gamma times v. So now the Fokker-Planck equation, one can write the Fokker-Planck equation, no, explicitly. What it is going to be delta f vt del t equals to, remember the first one was minus del del v of m1v. So minus minus will cancel, give you plus. And it you had this term del m2v. And this is your Fokker-Planck equation. And this is a very nice result. At least the result for M1V and M2V it will be very useful when you do in the, and go to the next class and do something else. We'll stop here. We'll start from here in the next class. But if you have question, you can ask me questions. I have sent you one collection of notes by Devshankar Ray. Did you see that in the Moodle? How many of you have seen? Are you guys there?
Yes, sir.
So how many of you have seen this, the notes which I have shared on Moodle?
Yes, sir.
Yes, please go, and because that note is very nice, but there are many typos. So I'm very careful while I doing derivation. Hopefully I did not do anything wrong. Things are fine. Okay, so I think we'll stop here. I hope you are following this part. This is time-dependent statistical mechanics, extremely important in chemistry, in physical chemistry. After maybe next to next class, I'll show you some examples. Maybe next class also I can show you some examples, and they will talk about barrier crossing problem, which is called Kramer's problem, which is again very very important in physical chemistry and physics for chemical reaction, and a model for chemical reaction or physical process which has a barrier crossing with dissipation. And we'll connect that to your known theory, to chemist, transition state theory. Okay?
I just
Yeah.
have one to point out, which is that in coordinate space Brownian motion, which is Einstein's statement, there is only a del 2 del x square, second derivative in coordinate.
Yes. But this drift term was not there. Drift term was not there. Yes. But in velocity space, there is a drift term. There is a drift term. See, okay, I have to. There is a drift term. See, the point is as follows. Whenever you see now, when you go to Einstein expression, your second derivative is exposition. It basically means that is coming from inertia. Sorry, I'm wrong. In Einstein's formulation, in coordinate space, there is no inertia. You have second derivative in position.
Yes, it is pure.
Yeah, this is called overdamped because the corresponding Langevin equation is overdamped. Viscosity is very large, inertia is zero. Is neglected, is dropped. But here you have only in velocity space. In the next class, you will do in the phase space where you have position and momentum. And you will see what happens to this Fokker-Blank equation. You will have something known as Cramer's equation. And eventually you will use that Cramer's equation to solve this Cramer's problem, which is barrier crossing problem. Okay. So this, because your delta average is zero in the coordinate space, but your delta average is non-zero in the velocity space. Your average jump delta is non-zero in the velocity. There is a drift. There is always a drift in the velocity space. Okay, but not in the coordinate space. Because when it jumps with the velocity, no? The jumping probably depends on the velocity.
Yes, yes. Got it.
But in position space, your jumping probably does not depend on that instantaneous position. It depends on instantaneous velocity. So it will accumulate, and average delta will be non-zero. So we'll stop here. Okay.
Okay, sir. Thank you.
Yeah. So we'll stop here and we'll stop recording.